Welcome to another chapter in forensic toxicology. Here's a beautiful picture of part of the Oklahoma Christian University campus. Looks like it's sunset. We become just by performing just actions, temperate by performing temperate actions, brave by performing brave actions. Aristotle said that many years ago. Okay, we're going to be looking at chapter 5, specimen preparation, and the remaining chapters in methodologies. And these are, for the most part, general areas of methodologies that we're going to discuss before getting into the analytes of our course. Things like alcohol, benzodiazepines, opioids, cocaine, cannabis, and so forth. So we're going to cover general principles of these items: specimen preparation, spectrophotometry, chromatography, immunoassay, mass spectroscopy, methods validation. All of these are very important to all the various analytes that we're going to look at. So let's jump into specimen preparation. In order to do a valid analysis, we have to adequately prepare the sample. We will mention these aspects of specimen preparation, all the way from aliquoting techniques, types of specimen preparations that exist, gas phase sampling for gases and volatile liquids, protein preparation, protein precipitation, specimen digestion for inorganic determinations, liquid-liquid, back extraction techniques, solid phase extraction, solid phase micro-extraction, esoteric isolation techniques. We'll touch on all of those. But first, specimens must be properly sampled and aliquoted in order to have any hope that the test results will be valid and reliable. The word aliquoted maybe is a somewhat an unusual word. It's often used in chemistry and analysis sciences, and it means to be fractionated into exact amounts with equal concentration, so that when you pull out an aliquot of a sample, you know that it will be the same as any other aliquot of that sample. This is not such a problem for specimens that are homogeneous at the time of sampling, such as plasma or serum. They don't require any special treatment before they're aliquoted. All sorts of body fluids, organs, tissue, bone, and hair are often sampled at autopsy or examination of the body. Whole blood, urine, brain, liver, gastric contents are often obtained. In more unusual cases, bile, vitreous fluid, internal tissues and organs such as the kidney, lung, spleen, hair, nails, bone, bone marrow, skin, fat tissue, and muscle are sampled. Depending on the actual testing techniques to be used, the amount of specimen that is needed will be determined before aliquoting begins. In other words, how much tissue does the protocol require? The smaller the sample amounts, the more savings of time, materials, and solvents. So it's better to improve analyte recovery than to use larger specimen amounts. If screening, take more specimen, 1 to 10 milliliters, but when using a specific test, take less specimen, 0.1 to 1 milliliter. Let's look at table 1, actually figure 1. This figure represents the analytical overview of a forensic toxicology case. In this chapter, we will be considering sampling and aliquoting, and the first step in isolating drugs from body fluids and tissues. And you can see sampling and aliquoting is right up here at the top, and then it mentions liquid and solid samples, and then we have to isolate the sample. Data collection comes next from various analytical techniques, and then data processing and interpretation must be done in order to tell anything from the data that's been collected, and then final report. Aliquoting techniques and types of specimen preparation. Solid and semi-solid tissues must be homogenized with water or buffer prior to continuing with a given protocol. For example, liver tissue has to be homogenized before it can be analyzed and tested. Aliquots are obtained by direct sampling with a pipette or by weighing. All analytical results contain a denominator of volume or weight to express concentration. So we have to make sure we have aliquots that are valid. Units that are used include milligrams per liter, micrograms per liter rather, milligram per kilogram, and gram per 100 milliliter. Let's talk about gas phase sampling for gases and volatile liquids. Gases. Specimens containing gases or volatile liquids should be frozen and secured in plastic or glass containers and held frozen until ready for analysis. This will prevent gases such as methane, ethane, propane, nitrous oxide, nitrogen, phosgene, chlorine from interfering with preserving the samples. Preparation of gas standards requires that pure gas be added to blood until saturation. The test blood results are compared to saturation concentrations in the literature. Such determinations are approximate because gas solubilities in blood are temperature and pressure dependent. Some gases can be measured using GC mass spec with injections of headspace. Let's look at volatile liquids a little more. Ethanol is the most frequent analyte in forensic toxicology, and certainly it is a volatile liquid at room temperature. It follows Henry's law. It can be analyzed using GC because of this. Henry's law can be simply stated as the following. At a constant temperature, the amount of a given gas dissolved in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. An equivalent way of stating the law is that the solubility of a gas in a liquid at a particular temperature is proportional to the pressure of that gas above the liquid. Henry's law has since been shown to apply for a wide range of dilute solutions. Other volatiles include acetone, isopropanol, methanol, ethyl acetate, propanol, 2-butanone, and dichloromethane. General methods for analyzing ethanol can be as follows. You pipette 0.1 to 1 ml of blood or urine into a sealable glass vial that is 5 to 20 milliliters in volume. Then you add an aqueous internal standard. It might be 1-propanol, 2-butanone, or acetylnitrile of a standard concentration. The internal standard must be separated from ethanol and other volatile substances easily. Next, you put a sealed vial into constant temperature bath, 30 to 50 degrees Celsius, for a specified time to allow partitioning of the ethanol and internal standard between the aqueous phase and the air space above the liquid phase. The heat will cause the ethanol and internal standard to go into a gas phase or headspace above the liquid. Next, you sample a measured volume of the headspace and place into the GC column. It is important to note that any volatiles that the person may have been in contact with since they can interfere with GC determination of ethanol should be noted. Okay, here is another major area of sample preparation, and that is protein precipitation. Proteins make up about 6% of plasma and greater than 50% of liver and other organs by weight. Proteins need to be precipitated before extracting and concentrating drug substances that are in these tissues. Removing proteins makes the preparation cleaner. Figure 1 on the next slide shows when protein precipitation can be done. Of course, we saw this slide earlier, but you can see up here under liquid, optional protein precipitation, also solid, optional protein precipitation, or tissue digestion. So early on in the whole process of analysis, protein precipitation can be done. Protein precipitation reagents can include Organic solvents like acetone, acetonitrile, methanol can include zinc sulfate and methanol, 5-sulfosalicylic acid, perchloric acid, trichloroacetic acid, sodium tungstate, and ammonium sulfate. Once the protein is precipitated, the sample must be filtered or centrifuged. Since some drugs get trapped in the precipitate, it can be washed with hot water or hot dilute hydrochloric acid. Protein precipitation is approved for tests that require a non-particle aqueous solution that is to be treated with a color-producing reagent. The supernatant is treated and must be particle-free. This is done in a colorimetric test used for salicylic acid, aspirin. Trender's reagent is used that causes protein precipitation and color reaction at the same time. Some drugs are more easily hydrolyzed by heating with acid or basic conditions. They need to be extracted without protein precipitation or with the use of mild precipitation reagents such as zinc sulfate, methanol, without heating. Specimen digestion for inorganic determinations. To test for inorganic poisons such as arsenic, cadmium, mercury, lead, and other metal ions, blood and tissues must be digested so all the organic material is oxidized away or burned away. This leaves a clean inorganic residue that can be analyzed using atomic absorption spectrophotometry, atomic emission spectrophotometry, and on and on. Digestion involves weighing out 1 to 5 grams of specimens such as nails, hair, soft tissue, bone, and then digesting it in a mixture of sulfuric, nitric, and perchloric acids. It is then heated, emitting sulfur trioxide fumes, SO3. Now spectrophotometric techniques can be used. Arsenic, cadmium are not analyzed by all forensic labs, but blood lead levels are often done by most state departments of health in the U.S. Enzymatic digestion is used for acid labile and strongly protein-bound drugs. The proteolytic enzyme subtilisin, it's subtilisin, Carlsberg, is commonly used. 1 milligram of enzyme per gram of homogenized tissue is incubated at 55 degrees Celsius for 1 hour. We'll stop right here at this point.